Quick recap. The key thing to remember is this, okay, which we have highlighted in yellow. The axis rotate with the what? Object. Okay, so that's where we can find our IY prime and our IZ prime easily. Okay, if it is from the horizontal and vertical axis, yeah, it's more difficult to identify the second moment of area. Okay, so that's why it's relative. The y and z axis rotate. Okay, with the structure. Okay, so key thing to remember over there. Any questions so far? Are we okay? We are fine. Okay, I don't hear anything. Okay, so this is one. Okay, so the next topic that we're going to go for. So we have completed centric unsymmetrical bending. Okay, so the next thing that I'm going to go for is eccentric. Okay, so the next one is known as eccentric. Now it's symmetrical. Okay, so now if I say the word symmetrical, unsymmetrical, you guys will be very familiar. Okay. Question for you guys. So if it's symmetrical, what's going to happen? Anyone? Just to see, can you remember if it's symmetrical bending? What does it actually mean? Anyone? How do you identify whether is it symmetrical or unsymmetrical? What's the most obvious things to find out?
If stress x alpha equals stress x beta.
Okay, yep. So that is what we call, you're absolutely right. So the left hand side and the right hand side stresses about the vertical axis is the same. Okay, it's symmetrical bending. Another way to look at it is in symmetrical bending. Okay, the resultant moment can either be on the y or z axis only. Okay, so by looking at the resultant moment, if it's only on one axis, only, so i.e. you have my and you don't have mz, it's symmetrical bending. Okay, or if it's mz and no my, it's symmetrical bending. Okay, now let's look at what do I mean by eccentric now. Okay, so what do we mean by eccentric? The eccentric usually mean crazy in human terms, right? Right. So again, you have all these images, okay, on Avenue to Learn. Right. So over here now, what we see now is a structure, okay, under eccentric bending. Okay. So let me write up the formula form first. So what we have is I'll draw transformation. This is our x. This is our y, and this is rotation about z, right? So from here we can, the formula to use is stress x is equal to P over A, or I'll write that this is equal to Px over A, okay, minus by Mz over Izz multiplied by Y, right? So as you can see, for this case is symmetrical bending because we only have moment about one axis, okay, and that is your mz axis, as you can see down here. So that's why this is how we identify whether is it symmetrical or non-symmetrical. Right. So with this definition, right, if you look at this structure, All right. This is where we call our PX. Okay. I will label this as my PX. And our copper prime. Now, question: where were the if this were to be an actual structure that has been loaded, where would it actually fail? Anyone? Is it point A, point D, point C, point E, or point B? Anyone, please? Where will the structure fail?
Point D and E.
So what you're saying is in between, yes or no? Right? So
Yeah.
we are going to make the assumption that it's going to be exactly at the center, assuming that the material is homogeneous, everywhere have the same property. So this is the point of failure. Okay, so I'm going to shift this a bit. I'm going to shift this down a bit. Right? So over here, this is where failure will occur. Right? Failure will occur. Okay. So if you load a structure in such a manner, right, the structure will tend to deform. Okay. So how the structure will deform, I'm just going to draw one half of it. So how the structure will deform. So I'm drawing the deformation pattern. Okay. So this is how the structure will deform. Okay. So this is our deformation pattern. Okay. So what you will see over here, this is a pure structure, a pure deformation for symmetrical bending or for bending. Why? Because it's a smiling face configuration, yes or no? So what we have over here, down here, is our center of curvature again. Right? And if we look at the moment vector, right? So our moment will be acting this way. Right? So this is our MZ. On the other side, there's also a moment acting due to MZ. So now you ask me, Eugene, why is there a MZ? Okay. So moment, so before we go on, moment will be equal to force multiplied by perpendicular distance. Right? And the point of interest is at point C. Right? It's at point C, is our point of interest. Right? So relative to point C, right, which is also the location of the geometrical centroid. Okay, I highlight geometrical, okay, because centroid is usually been discovered based on geometry. Okay, so the moment, okay, the moment, so therefore the moment about z is equal to px, right? Force multiply the distance, and the distance what we get is d. Okay, so as I said, where point D is, where this line is drawn, okay, it's at its geometric centroid. Okay, it's at its geometric centroid. Okay, so as you can see from the moment vector mz, again we apply what I taught you last week. Okay, the head of the bending moment vector, this is equal to compression. The tail end, this side will be in what? Tensile. Still, the rules still apply. Okay, only the formula changes, the rule still what? Apply. So I don't want you to worry about if this is plus or is this minus. Don't worry. Okay, don't worry about it. Now, going back to the formula, okay, going back to the formula where we have px over a minus mz over izz multiplied by y. So we know, right, based on this diagram, based on Newton's third law, right, we cut the structure into half. Right, we cut the structure into half because we know failure will occur at point where? Point C. Okay. So if over here we have P prime, okay, by you applying Newton's third law, action equal to reaction, same in magnitude, different in direction, you have F over here. Okay, it has to react, yes or no? And because of how the moment is applied, so this is moment about Z, again Newton's third law. That's why the moment is going in this direction over here. Action equal to reaction. Same in magnitude, different in what? Direction. Okay. So if I were to write down the formula again, so Pz or stress in the Z direction equal to Px over A. Okay, so F over here is also equal to Px. Now, so for this case, what do I mean by that? This is calculating the axial load. Okay. Okay, this is the axial stress. And then the next one is minus mz over izz multiplied by y. This is due to the bending stress. Okay, that is due to the bending stress. Now, now what we're going to do is we're going to sketch. Okay, we're going to sketch the stress profile. Okay, so for 3A03, we calculate more distribution. Okay, we don't just calculate average value. Okay, I want you to see the difference between what we are doing now compared to what you learned from 2P. 2P, you just take average, right? No, now we are calculating distribution. Okay, so now, so assuming that our cross-sectional area is a rectangle. Okay, so I'm going to view it from another angle now. Okay, so now we are going to view, watch my transformation. Okay, so this is my transformation over here, right? So I'm going to look at the end view now. So I'm going to put my eye over here. Okay, we're going to look at our end view. Okay, this is supposed to look like an eyeball. Okay, so this is your eyeball, this is your eyelid. Okay, so if we look at the end view, now the transformation goes like this. Okay. So this is our transformation. This is our Y, and this is our Z now. As I said, I'm going to make an assumption is that we have a rectangular cross-sectional area. Okay, so we're going to have a rectangular cross-sectional area. All right. Okay. So based on what we see over here at the top, right at the top down here, is under compression. The bottom out here is under tensile. Now this is due to bending. Okay, this is due. So if we were to draw the stress distribution, right, based on what we see down here, so the px is going to be what? Tensile. Yes or no? It's going to pull the material away. So it's going to be tensile. So I'm just going to draw this now. So this is our stress x. Okay. And this is our y. Right. And then at this point over here, this is going to be our px over a. Okay, that is our px over a. So now we have a tensile. Okay, so this is, oh, I should not draw tensile so much. It's going to be up to here only. Okay, so this is our stress profile.